The good news is that nucleate boiling problems are mostly plug and chug. The bad news is that there's a whole lot of plugging before you get to actually chug. So for this example problem, we've got hot gas flowing through a boiler, and then water is going to be the fluid that is boiling. So we're trying to find a couple of different things. The main thing you're looking for is the rate of heat transfer from the gas into the water. Once we find heat, then we can find the rate of evaporation, that is how quickly the liquid water turns into steam. Apparently your TA Indiana doesn't really care about the other two parts, but we'll carry on and also find the ratio for the current heat flux versus the critical heat flux. And that's real important to know how close you are to burnout, right? The critical heat flux is the point where you can have an instantaneous and disastrous rise in temperature. So having a large gap, like a safety boundary before you get there is pretty important. And so along those lines, we'll also find out what the temperature is at the critical heat flux to, again, figure out how close we are to that value. So based on my picture, it looks like we've got a temperature of the water of 150 degrees, and I will assume that we are in a situation of nucleate boiling. Nucleate boiling is the regular, normal boiling, just like a pot of water on the stove where you have water touching the hot surface. The alternative is film boiling, where you have steam itself touching the hot surface. Unless your problem statement specifically tells you you're in film boiling, assume that it's probably almost always going to be nucleate boiling. Now normally, water would boil at 100 degrees Celsius, so this 150 tells us information that this system is pressurized. Water will boil at a higher temperature when it's at higher than atmospheric pressure. And so, for example, if you wanted to avoid boiling, if you pressurize your system, you can make it so that you can get temperatures higher than 100 degrees without boiling. So here we go, the nucleate boiling equation, which I'll write down from the FE reference manual. And so you see there's only 13 terms we need to find before we can start plugging numbers into our calculator. That's not so bad, right? I mean, you know gravity, that's 9.81, only 12 to go. Right, so we're given the surface temperature of the pipe with the gases, 160 degrees. Our water is boiling at 150 degrees, making progress. And actually, I guess progress has stopped. So here we need to go back to the tables and actually look up some values. Fortunately, we'll be able to get a bunch of these from the tables in the back of your textbook. So the tables in the back of my textbook have even increments with Kelvin temperatures. So I'm going to cheat and use tables in a different textbook that have nice even increments for Celsius temperatures. And so at 150 degrees Celsius, I grab two density values, that is the density of a saturated liquid and density of saturated vapor. I'll also grab HFG, which you may remember from your thermodynamics class is the latent heat of vaporization. This is enthalpy, and it's the difference between Hg and Hf. So it's the amount of energy that it takes to take a saturated liquid up to a saturated vapor, right? That's the amount of energy it takes to evaporate water. So the value for Cp for liquid water is 4311 joules per kilogram Kelvin. But since my HFG is in kilojoules, I'm going to go ahead and convert this also to kilojoules so that hopefully all my units will work out. So mu is the dynamic viscosity. Usually when calculating Reynolds number, I use the other viscosity, kinematic viscosity. Looks like a Greek letter V. But this time you use mu. Okay, Prandtl number 1.16. So I put some check marks by my equations just to count how many terms I found and how many are left. From 13 that we needed to find, we're down to just 3 that are left. So we've got lowercase sigma, which is going to be the surface tension. CSF, which is like a coefficient that accounts for the two surfaces, like what they're made out of. And then an exponent n. So looking at CSF, this is a coefficient that represents the interface between your liquid and the solid wall. So in this case, water versus the stainless steel pipe. The table in my textbook doesn't have stainless steel listed in it, so between these choices, I will go ahead and assume that it's similar enough to copper, and so I'm going to grab this 0.013. And the same table also gives me the exponent n, which is going to be 1.0. And I'm writing these down as an assumption because, again, I'm taking kind of a leap here that steel is going to behave like copper, but just as long as you write it down as an assumption, then you're good, you're covered. And that just leaves surface tension. Now, if you want to just look up surface tension in a table, you can do that. But why would anyone want to do that when you could instead use a stupidly overcomplicated looking equation? I mean, whenever I think of the number 1.256, I always think to myself, this should be an exponent in an equation. What a perfect number to use as an exponent. And we do have all the information you need for this, right? Our boiling temperature for the water is 150, and we can look up the critical temperature for water, 647, plug in all the numbers, raise it to the 1.256 power, and don't go bother looking for that number on your calculator, right? My calculator has an x squared button. I definitely do not have a x to the 1.256 button. But if you've got an x to the y, you can type it in just like normal. I don't know why this is so funny to me, but all these equations are just so weird. So surface tension, 48.74, and this is also something to be careful about. This is going to come out in millinewtons per meter. So we make that 0.048 to get it back in terms of newtons. So now we've got all 13 terms in the nucleate boiling equation. So now we just plug in all 13 terms and chug-a-lug away on through with your calculator. So I'm plugging this in 3 different pieces instead of trying to do this as one gigantic expression. And I get to 410.4 kilowatts. And again, that's kilowatts because I was in kilojoules for my HFG. And if you want to see the actual unit analysis to sort of prove that this actually worked, I'm putting that up on the screen now, so you may want to pause the video. I'm not going to explain the whole thing. But yeah, go ahead and pause the video, take a look at all this unit analysis to see why everything cancels out and how you get to those final units. It is definitely hard to keep track of them when you've got things square roots, raised to the 3rd power, all this kind of stuff. But actually the units are not kilowatts, it's kilowatts per meter squared, right? That's the lowercase q dot is per unit area. So in order to get to capital Q dot, the actual power in watts, we need to multiply by the surface area. So we're given that there's 25 meters of exhaust pipe with a 5 centimeter outer diameter. And so surface area for a cylinder is the perimeter of the cylinder times the length. And that gets us to 1612 kilowatts as the amount of heat that's going from the hot inside of the pipes into the water that is causing boiling in the water. And that leads directly into the next step, find the rate of evaporation. And this is just a throwback to thermodynamics, right? HFG is the amount of energy it takes to evaporate 1 kilogram. So if our heat is in kilowatts, our mass flow rate, kilograms per second, and HFG is kilojoules per kilogram, then we just have Q dot equals the mass flow rate times HFG. Or instead of mass flow rate, since this isn't exactly mass flowing through a pipe, this m dot would be the rate of evaporation. How quickly, how many kilograms per second are evaporating. A little bit of division, 0.763 kilograms per second. That's how much is being evaporated, about 0.7 kilograms every second. And now the part that you should care about, but your TA Indiana earlier did not care about, and that is the critical heat flux. So critical heat flux is vitally important because once this threshold is reached, right, this is the slope on the side of the boiling curve. Once you get to that peak, if you increase the amount of heat, just one morsel more, just 1 unit of energy more, you don't take a nice gentle ride down the roller coaster. You take an instantaneous jump all the way to the right side of the curve. And that's basically like nuclear meltdown, right? This is a drastic jump of potentially thousands of degrees increase just from going one tiny bit extra amount of heat flux. So for any real world boiler, you want to make sure that you're operating at a sufficient safety buffer below the critical heat flux. So I'll start by grabbing Q dot max out of the FE reference manual. At first, you'll be somewhat relieved to see a bunch of terms that we already looked up. HFG, surface tension, gravity, density, we already have all of these. But there's a new coefficient in front that we are going to have to talk about. And this coefficient is going to be based on the shape. So when boiling happens at a surface, you turn a bit of water from that surface into vapor. And ideally that vapor leaves the surface and is replaced by new water. Well, at the critical heat flux, that process is happening as fast as it possibly can. And how fast that could happen is going to be dependent on the shape. So it will happen differently if your surface is completely flat versus if your surface is a cylinder. If you have a round surface, imagine on the bottom side of that cylinder, the vapor bubbles have to take a different path to sort of escape the surface. And that's going to affect the critical heat flux because you'll essentially reach the peak a little bit lower because the bubbles have a harder time escaping. So the FE reference manual, if you flip to the next page, has a little table for values for this CR. And they're going to be dependent on a dimensionless length or a dimensionless radius in the case of a cylinder. And as an example, if it turns out to be a large horizontal cylinder, we would get a value for this coefficient of 0.12. But the textbook that I use by Leinhard has a more comprehensive table with a lot of additional shapes. And using this table, you have a coefficient of 0.131 times the coefficient listed in this table. But either way, if you want to use my textbook or the FE exam manual, you're going to first have to calculate this dimensionless radius. And so this dimensionless radius is not actually part of the equation itself. It's just used to analyze the geometry to see what sort of configuration we're in. And just another plug and chug equation. I already have surface tension, gravity, and my two density values. And this gets me to a dimensionless radius of 10.7. The reason this dimensionless radius is used is because the size of an object is dependent on the fluid as well as just the size. So envision you have a very high surface tension. So a very large surface tension will allow fluid to stick more easily to a very small radius curve, whereas a much lower surface tension would make it harder for a fluid to stick to a really sharp corner, like a real small radius curve. And so knowing just how big or small the radius of a cylinder is does not alone give us enough information without also knowing details of the fluid wrapped around it. And so this dimensionless radius is how we determine big or small based on both the fluid and the shape of the object. So plug and chug our radius of 0.025, half of the diameter, right? Also plug in surface tension, gravity, densities, and we get a dimensionless radius of 10.7. And this then qualifies as a large radius, which in my textbook gives me a value of 0.9, so 0.131 times 0.9, which by the way is very close to the 0.12 that I would get from the FE reference manual. It's actually just an extra decimal place. So plug everything into the Qmax equation. Again, a whole lot of plug-in for these surface nucleate boiling problems. And I get to a value of Q dot of 1818. And I keep writing this down wrong. This is not actually kilowatts. This is kilowatts per meters squared. The lowercase q dot is per unit area. So this value is comparable to the 410 that we calculated earlier, not the 1600. So 410 divided by this 1800 gives us 0.226, meaning we're only about 22.6% of the way to critical heat flux. So that leaves a pretty strong safety buffer. But how big is that safety buffer really? That seems quite a lot, like we would need 5 times as much heat flux. How much would we have to increase temperature to get there? That might be the more useful problem to solve. So I go back to this big, gigantic 13-term equation that we started with, and instead of plugging in the 410, I'm going to plug in the new 1818. I'm going to solve for what would surface temperature of the pipe need to be in order to get us to this 1818 kilowatts per meter squared lowercase q dot. And it's a little bit scary to see that the temperature is only 166 degrees. A 6-degree increase in temperature from 160 to 166 would increase heat flux by like 4 to 5 times. So even though it looked like we had a humongous safety boundary where we were only using 22% of the critical heat flux, we could actually reach that value by only increasing surface temperature by a mere 6 degrees. Since the amount of heat due to nucleate boiling is based on delta T cubed, small increases in delta T can result in big increases in the amount of heat transfer due to boiling. And so to re-emphasize how this boiling curve works, once we get to the critical heat flux at this 166.4 degrees, if we're able to control the temperature of the pipe, if we increase temperature just a little bit more, we'll head down that curve. Increasing temperature a little bit more will mean that we start getting into film boiling where there's actual water vapor on the pipes, and that's going to lower the amount of heat transfer, and that becomes kind of a safe situation, although it's not advantageous for the purpose because we'll get less boiling. However, if instead of controlling temperature, if the thing that we're controlling is the amount of heat that is sent through the system, then instead of going down and right on the curve, we instead go up on the curve if we increase heat flux. Well, the only way to go up is to jump all the way to the right. We would skip this entire dipsy-do on the curve, and the surface temperature of these pipes would immediately jump to like 1,000 degrees Celsius. And that's basically how in a nuclear reactor you get a meltdown, right? The uranium in the core is constantly emitting heat, and so if you go just past that with just a little bit more heat, you jump all the way over there and meltdown. I think that's enough plugging and chugging for one video, but if you're ready to keep going, then click on the video up on the screen. That's going to be the best one for you next.